In April of 2017, all the dishes in the Event Horizon Telescope swivel, turn, and stare at a galaxy 55 million light years away. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole.
In their intrinsic elegance, Einstein's equations forever transformed our vision of space and time. Bridging the realms of mathematics and physics, general relativity concealed a new conception of the universe. And although no one realized it at first, his formulas harbored a dark secret. The mathematics predicted that after the death of a massive star, when the foundations of reality crumble under the relentless force of gravity, space-time could collapse into an infinitely small region. The architecture of the cosmos fractured at a single point, a singularity from which an invisible monster emerges with the power to destroy worlds, stop time, and drain light from the universe. Taken to their limits, Einstein's equations predicted the existence of entities that would later be named black holes. Guardians of the dark that in that corrupted heart enclose the place where all paths end. In that singularity, all the laws that govern the behavior of the universe collapse. A realm where the quantum world and the realm of gravity meet. Where all forces, with gravity finally being strong enough, are unified. And like a dark well in the universe, everything is drawn by its gravitational power, faster and faster like a river accelerating in its course. With each passing moment, escaping the current becomes more difficult. Fleeing from that heart becomes increasingly challenging. Until inevitably there comes a moment when it no longer matters how fast you swim. You can no longer beat the current. A waterfall has formed in the fabric of space-time. Nothing can escape the gravitational tyranny of that singularity. That point, that place of no return, is the event horizon. Everything that crosses that boundary is lost forever. Not even light can escape. Photons plunge into the abyss. The boundary between the universe we know and the one hidden in the dark depths of a black hole. The empire of darkness, the place where there is no beyond, and that the universe hides under its own shadow.
Durante mucho tiempo los agujeros negros fueron considerados simples curiosidades matemáticas, cuentos que emergían de jugar con las ecuaciones de Einstein pero que no podían existir en la naturaleza. El universo de alguna forma tenía que prevenir su formación. Sin embargo, casi 60 años después de la publicación de la teoría de la relatividad general, dimos con la primera evidencia de su existencia.
In the 1960s, astronomers detected a peculiar source of X-rays 6,000 light-years away, which they named Cygnus X1. All observations indicated that the radiation was emanating from a massive star orbiting something invisible. Immediately, rumors that it could be a black hole spread throughout the community, generating a deep division among scientists worldwide. Something was roaring from the depths of the galaxy, a powerful source of X-rays that, at its heart invisible to us, could be the first specimen of this family of entities. After years of debates and speculations, finally, in the spring of 1971, more exhaustive measurements of the Cygnus X1 system showed that the star was orbiting around that center of mass with an extremely short period of just 5 days. This very high velocity could only be explained if it was trapped in a gravitational dance with a body of at least 6 solar masses. And there wasn't a single astronomical object that could be that massive. Only one option remained: It had to be a black hole. A prince of darkness that, by devouring a blue supergiant star, was creating the bright source of radiation we had been detecting for years. Thousands of light years away, we had captured the first evidence of its existence. The consensus that black holes were a reality became absolute. The discovery of Cygnus X1 caused a whirlwind in the world of astrophysics, sparking a deep interest in these bodies. A new era had begun. In the years and decades that followed, we found thousands of black holes. They had always been there, hidden in their own shadow. We were delving into the empire of monsters.
Sin embargo, todas las evidencias sobre su existencia eran indirectas. Observar estrellas orbitando alrededor de una gran concentración de masas, captar emisiones de radiación de alta energía, detectar los jet relativistas que emanan de los cuásares, o los efectos gravitacionales que generan sobre la luz a sus espaldas. Pero no teníamos ni una sola evidencia directa, porque para ello necesitaríamos una confirmación visual. Y aunque implicara perseguir algo que lucha con todas sus fuerzas por no ser visto, hubo quienes confiaron en obtener esa imagen del abismo que encierran.
At the beginning of the 2000s, astronomers were driven by the desire to observe the event horizon of a black hole. This would be the first direct evidence of their existence and the absolute confirmation that what Einstein's equations described was precisely what occurred in the darkness of nature. We had identified many bodies that seemed to be and behave like black holes, but we had never seen one. Without that image, without that irrefutable evidence, we couldn't be sure they existed. The photograph of a black hole was going to turn theory into reality. For the first time in history, it would allow us to look these monsters in the eye. Excited by the prospect of an ambition that many considered impossible, American astrophysicist Shep Doeleman laid the foundations for a project with a very clear goal: to obtain the first image of a black hole. To see what cannot be seen, to contemplate the nature of one of these beasts, approaching the heart that holds the answer to all the enigmas of the universe. By definition, a black hole is invisible. Light cannot escape from it. Everything that has fallen into the abyss is lost forever. The universe is hiding it. But something in it plays in our favor. In its fierce greed, the intense gravity attracts dust and interstellar gas into an increasingly faster orbit. The extreme gravitational power of the entity traps material in an eternal fall toward its depths. A turbulent path, at speeds that represent a significant fraction of the speed of light, where temperatures reach hundreds of millions of degrees. An accretion disk around the beast that emits light detectable by our telescopes. But this accretion disk does not reach the gates of the abyss. That stable circular orbit rests relatively far from the boundary, at about 3 Schwarzschild radii, which is the radius of the black hole's event horizon. This is the innermost region where matter can navigate. If it crosses that distance, it quickly falls to the place where all paths end. Observing the accretion disk was not enough to see the true nature of the monster. Black holes at the centers of galaxies are bathed in plasma. There is light surrounding them everywhere. And with such immense gravitational dominance over the fabric of space-time, they are capable of altering the path of photons. Light is curved, and a marvelous effect emerges. At a certain distance, approximately 1.5 Schwarzschild radii, photons can enter unstable circular orbits. The particles of light are temporarily trapped around the black hole before finally escaping or being swallowed by the singularity. And right there, at the edge of this boundary between escaping and falling, light forms a bright ring around the event horizon. a photon ring that would surround a central dark region. This would bring us practically to the event horizon and, above all, show us the shadow of the black hole. If we could see that ring, if through it we found that sphere of darkness, then we would have the image of a black hole.
Todas las simulaciones mostraban esta región de sombra bien definida, el horizonte de sucesos en sí mismo. Todo lo que teníamos que hacer era echar nuestra mirada hacia uno de ellos y hallar ese anillo de fotones, generado por la lente gravitacional del disco de acreción a su alrededor. Tendríamos ante nosotros una esfera de oscuridad, así que todo lo que teníamos que hacer era buscar esa sombra en medio de la luz.
Progressing on these theoretical foundations of what still seemed a utopia, we discovered that at certain wavelengths, the entire accretion disk would be transparent. There would be no obstacles. We could penetrate that chaos of ultra-hot matter and descend to that photon ring. Let the light carry us to the gates of the abyss and show us that shadow. On paper, nothing was impossible, although it was clear that sooner or later they would face one of the greatest technological challenges in the history of science. The path to the monsters was paved. It was time to decide which path to follow. Naturally, the team's first target was the black hole reigning at the heart of our own galaxy. A beast whose existence was revealed by the strange and extremely fast orbits of stars navigating around something in the galactic core with a mass of 4 million suns. The gravitational whispers of Sagittarius A star, the emperor of the Milky Way. The black hole with the largest angular size in the sky, and at first glance, the clear target for obtaining that image. However, we soon saw that there were too many obstacles associated with it. Between us and the galactic center where it resides, there is an enormous amount of dust and gas that protect it like an opaque veil. Additionally, we know it consumes very little matter. Sagittarius A star is unusually peaceful, and that serenity worked against us in capturing its echoes. It was highly likely that we wouldn't find the shadow we sought there. We needed a plan B, and of the thousands of black holes discovered, only one stood out as a serious candidate. An entity lurking in the remote depths of space and time. 53 million light-years away, north of the Virgo constellation, rests an immense island of light, the elliptical galaxy Messier 87. A realm ruled by a furious king. A supermassive black hole with a mass of 6 billion suns and a diameter of 38 billion kilometers. So large that the entire solar system, up to the heliopause, could fit within it. M87 is also incredibly active. It constantly feeds on matter that not only causes jets of radiation to emerge from its poles, extending over 5,000 light-years. Its accretion disk burns and shines like hell. And if they were considering this target, it was because it could compete head-to-head with Sagittarius A star. The angular size a black hole occupies in the sky is a combination of its mass and the distance separating us. The black hole at the center of our galaxy is a mere 26,000 light-years away, negligible compared to the 53 million light-years between the Milky Way and M87. But being 1,000 times larger, that difference diminishes. The result is that in the sky, they have comparable sizes. Likewise, that colossal size means the matter around M87, already much greater than Sagittarius A star, takes 1,000 times longer to complete an orbit around it. Its accretion disk is much larger, but its appearance over time is more stable. Very different from our king, in whose realm things can change in a matter of minutes. Added to all this, being much more intense, the gravitational effects it would have on the much-desired shadow had to be much greater. And finally, its location in the sky was very favorable for observation, easily accessible from both hemispheres, and with no dust and interstellar gas between it and us. M87 was our best prey. If anyone was to give us that image, it was it. There was no better hope in the firmament.
Pero incluso con M87, donde todo estaba inusualmente alineado para su objetivo, el reto al que se estaban enfrentando no tenía ni un solo precedente. Imagina el cielo nocturno como una esfera que rodea completamente la Tierra. Un círculo completo equivaldría a 360 grados, y en ella cada grado puede dividirse en 60 partes iguales llamadas minutos de arco. La Luna, por ejemplo, ocupa un espacio angular de 30 minutos de arco. Con M87 no solo estábamos intentando ver algo que lucha por no ser visto, estábamos intentando captar la sombra de un cuerpo que en el cielo ocupa un espacio angular de 40 microsegundos de arco, 45 millones de veces más pequeño que la Luna. O llevábamos la tecnología a los más absolutos límites, o el sueño de esa imagen se desvanecía.
If we were truly going to capture the abyss, that intimidating shadow at the heart of M87, we needed impeccable resolution. Surgical precision that was only achievable by working with high-frequency electromagnetic waves. With them, not only sensitivity increases, but high-frequency waves also penetrate gas and dust more easily. If we wanted a detailed image, and if we aimed to penetrate through the entire accretion disk to the event horizon itself, visible light wouldn't suffice. Its frequency was too low. We had to work in the radio wave spectrum, specifically at a wavelength of 1.3 millimeters, corresponding to a frequency of 230 gigahertz. We weren't going to take a photograph in the strictest sense of the word. Visible light wouldn't serve us. The image would be constructed from radio signals. These millimeter waves would penetrate interstellar dust and gas, allowing us to observe the immediate surroundings of the black hole with what they hoped would be great clarity. The theoretical foundation was simple. A radio telescope had to scan that region of the sky, capturing radio waves emitted by M87, scanning the center of the black hole, hoping to see a bright region as it passes through the left side of the ring, a dark region when it encounters the heart of the monster, and finally, an increase in brightness again as it passes through the right side of the ring. With this, we would have the image, but in practice, all that simplicity vanished. The angular resolution of a radio telescope is its ability to distinguish between two-point sources of radio waves. It measures the level of detail it can observe. The better the resolution, the finer and more separated the details in the images. Improving angular resolution can be achieved in two ways, either by working at higher frequencies or by increasing the size of the radio telescope. Frequencies higher than 1.3 millimeters weren't feasible because the light would be blocked by our atmosphere or fall into the infrared spectrum. Therefore, the only alternative was to work with a large antenna. However, the maximum angular resolution achievable with a 100-meter diameter radio telescope is 6 arc-minutes. For M87, we needed an angular resolution of at most 30 microarc-seconds. With lower resolution, if we were observing the black hole, as we reached the right side, we would still be receiving light from the left side. We wouldn't capture that central dimming. There would be no shadow. We wouldn't have the image of the event horizon. We needed a sufficiently large radio telescope, or with current technology, we would never obtain that portrait of the abyss.
El problema es que era imposible disponer de un radiotelescopio suficientemente grande. Los cálculos revelaron que para llegar a la resolución de 30 microsegundos a la frecuencia de radio que tenían que trabajar, la antena tendría que medir tanto como el diámetro de la Tierra. Construir un radiotelescopio de 13.000 kilómetros de diámetro no era una opción, así que parecía que habían llegado a un callejón sin salida. Pero quizás sí había una forma de disponer de ese observatorio de tamaño planetario.
If having a radio telescope as large as the Earth was impossible, perhaps they could opt for the next best thing. In 2006, when the idea began to take shape and Shep assembled a first team to study the feasibility of capturing that image, they developed a master plan to achieve that angular resolution. If they couldn't have a planet-sized radio telescope, maybe they could turn the Earth into their observatory. By combining telescopes in Europe, America, and the South Pole, all pointed at the same point in the sky, they hoped to achieve that resolution. The foundations were being laid for what would be named the Event Horizon Telescope, the most ambitious project in the history of radio astronomy. Scientists aimed to create a network of 8 telescopes in Spain, Mexico, the United States, Hawaii, Chile, and the South Pole, capable of communicating and synchronously recording data that could later be combined to reconstruct the image. An array of observatories that together achieved the angular resolution theoretically capable of capturing the photon ring of M87. In a sense, they were creating a radio telescope with the diameter of the Earth, born from the combination of telescopes spread across the globe. To capture that image, all 8 telescopes had to aim towards the depths of that galaxy 53 million light-years away, extending to the realm of the black hole at its heart. Each piece of this system individually captured radio signals. Telescopes separated by thousands of kilometers observing the beast simultaneously, but without direct contact between them. As long as they could combine the readings from all observatories, they would obtain the pattern of constructive and destructive interferences necessary to achieve that 30 microarcsecond resolution. Each telescope was collecting its light, and as the Earth rotated, new measurements were being obtained. A meticulous scan that would later be pooled together. Data combined into a single signal to which image processing algorithms would be applied. Programs that would fill in the inevitable gaps, complete the reconstruction, and gift us with the image of the Guardian of Darkness.
Básicamente lo que estaban sugiriendo era como romper un espejo con un martillo, distribuir aleatoriamente los fragmentos por todo el mundo, grabar lo que se refleja en cada uno de ellos para después volver a juntarlo todo en un superordenador que recree lo que han visto en una sola imagen. Esto es lo que los científicos del Event Horizon Telescope querían y necesitaban hacer para retratar ese abismo en el espacio y en el tiempo.
Aware that the foundations were solid, that what initially seemed impossible could become reality, in 2009, the formal collaboration of the Event Horizon Telescope was established. At a meeting of various institutions worldwide held in Chicago, the project officially came into being. We were going after that image. The ALMA and APEX radio telescopes in Chile, the IRAM Observatory in Sierra Nevada, Spain, the James Clerk Maxwell Telescope, and the Submillimeter Array in Hawaii, the Large Millimeter Telescope in Mexico, the Submillimeter Telescope in Arizona, and the South Pole Telescope in Antarctica. 8 radio telescopes, over 200 scientists from 60 institutes across 20 different countries, all united by a shared dream. An ambition that would only materialize if they could make the operation of these 8 telescopes a perfectly orchestrated symphony. To link the radio telescopes, they would use a technique known as Very Long Baseline Interferometry, or VLBI for short. With VLBI, different antennas can work together, functioning as a single instrument. By combining the light from distant radio telescopes, they achieve a resolution comparable to having an antenna with the diameter of the distance between them. Unlike an individual observatory, radio signals wouldn't reach a central receiver to be summed up in real time. Each telescope recorded its signals with a time precision on the order of femtoseconds, 1/quadrillionth of a second, to later merge the readings through a supercomputer. The challenge was that up until then, all interferometry projects had linked only 2 radio telescopes. They needed to do it with 8. All working flawlessly and synchronized with unprecedented precision. Success or failure of the project rested on timing. Timing the signals was critical. The heart of the Event Horizon Telescope dream. The network was so large with a diameter similar to that of planet Earth that the emission from the black hole would reach each telescope at a slightly different time. Not to mention, due to the Earth's rotation, the relative position of the observatories constantly changed. These differences meant each telescope obtained a unique interference pattern. That alone revealed almost nothing. But by combining the patterns from all 8 telescopes, the image emerged. It was a meticulous craftsmanship built on this timing. If they couldn't record the arrival times of signals with an accuracy of 1/4,000,000th of a second, there was no way they could combine them as one. To capture that image, they had to measure time passage with unprecedented accuracy. And there was only one hope. The team had to spend $2 million from their funding to acquire the world's most precise atomic clocks. The 8 radio telescopes were equipped with what's known as a hydrogen maser, a device containing excited hydrogen atoms induced to fall to a lower energy state, emitting microwaves of a very specific wavelength. This signal, once amplified, was extremely stable, hence suitable for timekeeping in an atomic clock. Theoretically, if maintained at a constant temperature, a hydrogen maser would desynchronize by only 1 second in 10 million years. With this timing in their hands, the theoretical foundations of the project were closed. They had done everything within their power. It was time to gaze into the darkness. Everything was set for that date with history.
La complejidad de llevar a cabo esta interferometría con 8 radiotelescopios no podía ser mayor. Incluso con esos relojes atómicos tenían que tener en cuenta el propio movimiento de las placas tectónicas, sin olvidar que la propia Luna también afecta gravitatoriamente al mundo por las fuerzas de marea. Y todo esto sin poder ver los resultados a tiempo real. Estarán a ciegas almacenando datos. Solo cuando reúnan las lecturas de los 8 radiotelescopios podrán saber si el experimento ha funcionado. Pero nadie dijo que observar el corazón de las tinieblas fuese a ser fácil.
8 years after the official establishment of the Event Horizon Telescope, nearly a decade of instrument preparation and international coordination finally culminated in April 2017. They were ready to see if their dream would come to fruition or fade away before them. Shep and the team had a window of 10 days and needed a minimum of 5 nights of data collection to maximize their chances of success. But this wasn't a normal radio astronomical experiment. They needed perfect weather across all 8 locations. Each radio telescope had to operate flawlessly. If one failed, or if clouds obscured the view at any location, the chances of capturing the image were practically nil. They were at the mercy of nature, unsure if the universe would allow them to glimpse its best-kept secret or continue to shroud it in mystery. Fortunately, on the night of April 4th, the control center received news that all 8 radio telescopes were operational and the skies were clear at every location. Everything had aligned. The universe had granted them an opportunity. The veil between us and the darkness had lifted. They had permission to observe what had been hidden from view throughout history. The gates to this empire of darkness were open. After all the waiting, they were now gazing at the heart of a black hole. Across the globe, in perfect synchronization, the 8 radio telescopes were capturing signals from the reigning monster in M87. A total of 500 hard drives were storing millions of gigabytes of data. The required resolution was extremely high. To ensure reliability, redundant observations were made covering different angles and moments. All of this was done at a wavelength of 1.3 millimeters, which penetrates interstellar dust and gas, but also generates a massive amount of data due to its high frequency. Similarly, for crucial interferometric synchronization, the enormous volume of data had to be accompanied by highly precise timestamps. A massive amount of data was being generated every moment. Night after night, the symphony continued. Against all odds, the skies had gifted them the clarity they needed. Until finally, on the 5th night, the light from that cosmic beast was captured one last time. The scientists had 5 days of observations. They had done everything within their power. Now, there was only one last chapter in this story, bringing to life a chaotic ocean of data.
En total, los 8 radiotelescopios generaron 5 petabytes de información en las 5 noches de observación. Esos son 5 millones de gigabytes. Para poner en perspectiva lo que significa eso en términos de volumen, si alguien filmara toda tu vida en alta definición, suponiendo que vives 100 años, ese vídeo ocuparía 0,5 petabytes. Lo que habían almacenado eran 10 vidas enteras, filmadas de principio a fin. De largo la mayor cantidad de datos recabado en cualquier experimento de la historia de la ciencia. Pero entre ellos tenía que estar la imagen. Ahora ya solo era cuestión de encontrarla.
With that treasure stored in the form of unintelligible mathematical language, the hard drives from each of the 8 radio telescopes had to be sent to a processing center, where all the data would be combined, and if luck had been on their side, reconstructed into the portrait of the monster. The amount of information to handle was staggering. They not only had to measure each signal captured by the observatories, but also had to merge every wavefront from the 8 sets of data into a single faithful representation. They needed immense computational power. For this task, the MIT Haystack Observatory in Massachusetts, USA, and the Max Planck Institute for Radio Astronomy in Bonn, Germany, began receiving the hard drives. The volume of data was so large that it couldn't be efficiently transmitted over the internet. It had to be physically shipped. Within days, 7 of the 8 radio telescopes had delivered their hard drives. They were just waiting on one. Due to the southern winter, the Amundsen-Scott South Pole Station, where the South Pole Telescope is located, was closed. No flights could land or take off from the station. The data from the 5 nights of observation from the southernmost region of the planet were held until October. But finally, after a 5-month wait during which they still didn't know if the experiment had succeeded, with the end of winter in the South Pole and the reopening of flights, they could receive that last piece. The team now had all 8 sets of data. Using the magic of interferometry, supercomputers combined these 5 petabytes of information. Equipped with 800 CPUs connected via a 40 gigabytes per second network, they produced that single conglomerate of data. Everything was encoded in that code. It was time to unveil the light we had received from the darkness. Thus, on October 12, 2017, the Event Horizon Telescope team initiated what became known as the EHT Image Hackathon, an event gathering imaging processing experts from around the world. They worked together to combine and analyze the data collected by the network of radio telescopes. Participants, prominently featuring the role of young American engineer Katie Bowman, developed and refined algorithms that would transform raw data into a coherent image of the black hole.
El principal reto al que se enfrentaban es que no tenían la información completa sobre él. Era como si en ese lienzo tuviéramos algunos píxeles, pero no todos. El arte ahora consistía en descubrir cómo se veía la pintura completa sin tener todo lo que nos gustaría tener. Eso era lo que los algoritmos tenían que conseguir. La reconstrucción de la imagen del corazón del monstruo.
After months of work, of endless days adjusting image processing algorithms to ensure the reconstruction will be consistent, that what we are about to see is a faithful representation of what awaits at the heart of that distant galaxy. On June 5th, 2018, the teams announced they are ready. It's been over 10 years of effort, $50 million spent on the project, over 200 people dedicating their lives to that dream that seemed impossible. But the moment has arrived. We are prepared to reveal that image. The data enters the system and the algorithms are executed. Magic emerges before their eyes. The software is generating images. We are not seeing simulations. We are looking into the eyes of a beast hidden tens of millions of light years away. Portraits of M87 are being unveiled. And after several runs, suddenly, one particular image captures everyone's attention. As a gift from the universe, with astonishing clarity, the ring of light is shown in full splendor, the most visceral reality of that guardian of darkness. At its heart, the shadow of a place where all paths end, where light perishes and time loses its meaning. A marvelous portrait of the abyss, of the event horizon of an entity with 6 billion solar masses curving light due to its gravitational tyranny. They had obtained the image of a black hole. In it, we could travel to that very place. For the first time in history, we were seeing its nature. We were witnessing the struggle between light and darkness. Witnessing in that perfect shadow the path where light is lost forever. We had the first direct evidence of the existence of black holes. Confirmation that space-time, in the most extreme place in the universe, distorts in the same way Einstein's equations predicted. The image, though showing the photon ring and not the accretion disk, displayed the plasma orbiting around the supermassive black hole at the heart of the galaxy M87 with a period of about 2 days and in a clockwise direction. The bottom part is brighter due to the relativistic beaming phenomenon, which states that particles from a bright object in motion emit radiation in the direction of that motion. The black hole is rotating, so some of the gas is moving towards us from below at speeds close to that of light and separates at the top, hence the greater brightness in the lower region. Absolutely everything was as we expected to see. As a gift from the universe, the image was a reflection of what we had dreamed of for years.
La reconstrucción de la imagen había mostrado a M87 anclando gas bajo su dominio gravitatorio. Teníamos evidencia visual de materia navegando a su alrededor de camino al abismo. Y sobre todo, lo que de verdad estábamos buscando, la sombra en el centro del anillo. Era una certeza que lo habían conseguido. Así que ahora ya solo era el momento de compartir con el mundo esa imagen que demostraba que los imposibles no existen.
Keeping the secret since that July 2018 to verify the analyses repeatedly before shaking the foundations of the community. Finally, on April 10, 2019, the leaders of the Event Horizon Telescope convened 6 simultaneous press conferences worldwide to announce the discovery. The moment that all 200 members had dreamed of and doubted would ever come had arrived. It was their moment. The moment to show what had been invisible to us throughout history. Something the universe had jealously hidden. They were finally announcing that they had seen what was believed to be impossible to see. They had portrayed an abyss in space and time, taken the image of a black hole to, quoting directly, Contemplate a world conceived to be inaccessible. That shadow crowning the center was not empty. It was the heart of the monster. Resting our gaze upon it, we were seeing the place where the singularity rests. In that shadow lay the realm where new physics awaits. The purest darkness had never revealed so much, because all that time we had not pursued the light. What we truly craved was that portrait of darkness. The scientific and media repercussion was immense. The image of the black hole in M87 dominated headlines and front pages in major media outlets worldwide. Print media, traditional broadcast media, and social networks made the photograph a mass phenomenon. We were facing one of those moments that mark a before and after, an instant classic. A moment for posterity and a chapter of our era that future generations will look upon with admiration. It was much more than an image. It was something that amidst its light and darkness showed our ambition to explore what lies at the end of the world. What hides beyond the horizon.
En la sombra de un guardián de las tinieblas en los confines del espacio y del tiempo, estaba condensado ese espíritu humano de ir siempre más allá. Y otra vez habíamos demostrado que somos capaces de todo. El imperio de la oscuridad ya estaba a nuestro alcance. Habíamos conquistado un nuevo reino.
Years after what was already a historic date, the Event Horizon Telescope obtained the second image of a black hole. This time, of the king of our own galaxy. From the same observations in April 2017, they had the portrait of Sagittarius, a star. Inspected like M87, but with many complications in reconstructing the data, they had to develop new algorithms to handle the rapid variations in its environment. Years of work to average the variations and obtain a coherent image. But finally, on May 12, 2022, they repeated their success. We had the portrait of the gentle giant awaiting at the heart of the Milky Way, just 26,000 light-years away. With it, the second chapter in this hunt for the Guardians of Darkness began to be written. The two entities that current technology allowed to portray had been captured. But this is only the beginning of the story. There are still many seas to navigate. It is our obligation, as a debt to the universe that showed us what it had always hidden, to continue looking into the eyes of these bodies. Because it is in them, in the shadow of their hearts, that the answers to the big questions await. We have to continue shedding light on this empire of darkness. Contemplate the depths of that eternal abyss.